Hello everyone, and welcome to the section 1.2 lecture, which is on graphs of equations in two variables, intercepts, and symmetry. That's quite the mouthful of a section title, but we'll go ahead and get right into it. And in order to do so, the first thing we're going to talk about are graphs of equations. So you don't need to write this down just yet, but I want to paint a picture for a second. Is if I have x squared plus y squared equals 4, I'm just writing this down so we can visualize something. You may have already seen this in previous math courses before, but we know in mathematics that this defines the graph of a circle. Now, why is that the case? Why does that work? Well, that actually has to do with, so you may have heard that the rectangular coordinate system is also called the Cartesian plane, right? And that has to do with the famous philosopher / mathematician René Descartes. His last name looks like Descartes. But René Descartes, he was the first mathematician to think about the connection between an equation and a graph. And how he did it was this. So definition. A solution, sometimes people say, there's other verbiage of this, but a solution to an equation, to a two-variable equation is an ordered pair, x comma y, that satisfies the equation. Now, what do I mean by satisfies? So that's what our book uses, by the way. They say that an ordered pair satisfies an equation when they mean a solution. So, and what I mean by satisfies is that when you plug in this ordered pair, when you plug in whatever x value you have and whatever y value you have into the equation, you get a true statement. So you'll get 0 equals 0, or 10 equals 10, or 7 equals 7. Who cares? That's what a solution is. So as an example, a little quick example, the point 2, 9 is a solution to negative 2x plus y equals 5, but 1, 1 is not a solution. Now, why is that? Let's look at why. So, if I'm looking at the point 2, 9, that means that x is equal to 2 and y is equal to 9. If this were a solution to this equation, it would mean that when we plugged in x equals 2 and y equals 9, we would get a true statement. In particular, negative 2 times 2 plus 9, does that equal 5? And yes, it does. 5 equals 5. That's how we know that it's a solution. Versus, if we plug in 1, 1, that means that x is equal to 1 and y is equal to 1. But if I try and plug these in, we're going to see very shortly that that's not actually going to make a true statement. So negative 2 times x value, which is 1, plus our y value, which is also 1, does that equal 5? And if we simplify the left-hand side, we'll see that we get negative 1 equaling 5, and that is not a true statement. So that's what it means to be a solution to a two-variable equation. And this can be extrapolated to 3-variable equations, 50-variable equations, whatever you want to do. Now, how does this help us? Or rather, how do I go back to my point about René Descartes? Well, you see this point right here, an ordered pair x comma y. What René Descartes thought about was saying, well, okay, let's take all these x comma y values and we'll plot them on an xy grid. And that will be the graph of the equation. And that's precisely what it is. So let's go ahead and write that. So that's one more definition, is that the graph of an equation is the set of all pairs, ordered pairs, I guess. But you can write ordered if you want. X comma y that satisfy the equation. And so now we use this to our advantage. Now later on, we'll figure out new ways. We'll learn about the library of parent functions and all that jazz, and that'll help us graph functions much faster. That's one of the biggest things we do in this course is learn how to graph things faster. But for right now, this is kind of how we did in the old days. If we wanted to graph something, we just find all the points on the graph. So let's just look at an example of that real quick. So example, plot, or not, draw the graph of y equals x squared plus 1 by filling in the table. Alright, so the table, we're going to start right here, and so it's going to give you an x value, and then it's going to give you a y value, which is x squared plus 1, right? Our y value is x squared plus 1, and then that's going to give us our ordered pair, x comma y. So in particular, I'm going to choose the points -2, 0, and 1. Now we should probably plot more points than this, but this will be sufficient for our needs. So we're just going to pick several random x values, and you could. So you might be thinking, well, Phil, why didn't you start with x or y value and then do the x value second? And you see, the reason why I did that is that if we plugged in a random y value, then we'd have, like, let's just say for the sake of an argument, we chose y equals 7 or whatever. Then we'd have to subtract 1 from both sides, and then we'd have to take the square root. We get 2 answers, and that gives us more work that we have to do. Whereas if I just use the x value, I can just plug that in, and then I don't need to solve for y. It's already done for me. That's the reason why here. So in this case, y would equal -2 squared plus 1, which would equal 5. If I plug in 0, I'd get 0 squared plus 1, which is 1. And if I plug in 1, I get 1 squared plus 1, which is 2. By the way, feel free to, if you feel comfortable doing this in your head, I encourage you to do so. I don't need to, I don't really need to see this work right here. But anyways, that gives us the points -2 comma 5, 0 comma 1, and 1 comma 2. So, those are all points on our graph of this equation. Now, you might know that that's a parabola already. If you don't, that's totally fine. We're going to get there pretty soon. And so, let's go ahead and graph it. Now, I'm going to use a little piece of graph paper, but I encourage you to pause for a second and draw at least 6 tick marks everywhere on an XY grid. And boom, here's mine. Once again, modern technology, love it. And so I'll just plot all these points. -2 comma 5, that would be right here. 0 comma 1, that would be right here. And 1 comma 2, that would be right here. Now, I'm plotting these just to make it look prettier, by the way, but I can guarantee you the point -1 comma 2 and the point 2 comma 5 are also on this graph. And you wouldn't know, like, right now how to graph this without plotting a million points. So that's what, we're going to kind of skip that for now and just draw what the shape would be if you take my word for it. But I guarantee you if you plugged in, every x value between -1 and -7 and 1 and 7, I guarantee you this is the shape that you would get. So, that's the graph. And with that, we will move on to a property about graphs that we are very interested in mathematics, and that would be intercepts. And that's what we'll write. So we'll talk about x and y intercepts. So the first thing would be a definition. What is an x-intercept or a y-intercept? So an x-intercept is a point where the graph intersects the x-axis. And a y-intercept is a point where the graph intersects the y-axis. So that's the definition of an x and a y-intercept. It's a point where they cross their corresponding axes. And they will like, as we go on further and further, we'll know more properties. I'll try and highlight the connections between certain concepts and what x-intercepts and y-intercepts do. But for now, we just want to be able to find them. Now, there's two main ways we can find them. And the first way is visually. So I'm going to do a visual example to start off with. So I'm going to call this a visual example. And it's going to be find the intercepts. And as a small aside while I'm doing this, and I'd encourage you, so I'm going to do the whole graph thing. I'd encourage you to make a graph grid with at least 2 graphing grids, each one with 5 tick marks everywhere. 5 tick marks everywhere. And so while you're doing that, I'm going to tell you that when it says find the intercepts, that means find all of them. Find the x-intercepts and the y-intercepts. If it doesn't specify x or y, it means both. I hope that makes sense. So part A and part B, I'm going to do the same thing. Right there, okay. For these 2 graphs, for the first one, I want you to plot the points -4, 0, 0, 3, 6, 0, and -1, 0, -1. So once again, that's -4, 0, 0, 3, 6, 0, and 0, -1. And then you want to kind of make a little bit of a UFO shape of sorts, like this. It's not perfect, but that's what it is. That's the first one. And the second one, I want you to plot the points 3, 0, 5, 2, 3, 4, and 1, 2. So once again, that's 3, 0, 5, 2, 3, 4, and 1, 2. And I want you to kind of make a little polygon, like a little, it almost looks like a square. I think it might be, actually, yeah. Okay, so let's go ahead and find the x and the y intercepts. So, the x-intercept for the first graph, there's going to be the places where it crosses the x-axis, which is precisely right here and right here. So that's going to be 6, 0 and -4, 0. Some books, and our book will do this, and sorry, I have a bad habit of doing this because I like to label my x and y intercepts as ordered pairs, as points, because they are actual points. But a lot of books will just say, instead, they'll say the x-intercepts are x equals 6 and -4. Because if you specify saying an x-intercept is 6, it's implied when you say that the y value is 0. So our book will ask us to just write the x-intercepts as numbers, but please note that they are also points. It's very, very useful to know that it's a point later on in some more tricky problems. But anyways, back to the problem at hand. The y-intercepts are going to be where it crosses the y-axis, which in this case would be right here and right there. That is to say, 0, 3 and 0, -1. Let me make that a little bit better. Or, once again, you could say like y equals 3 and negative 1. Those are the y-intercepts. Now, similarly, on this one, x-intercepts are where it crosses the x-axis, and we see that only happens once at 3. So I may slip up from time to time, but I'm going to try and make sure I can stay consistent with the way the book says it. So the x-intercept here is x equals 3. And what about the y-intercepts? Well, if we look at the graph, if we look at the y-axis, our graph doesn't touch that. So there's no place where it crosses the x, it intersects the x-axis, and therefore there are none. There are no y-intercepts. I bring this one up as an example to remind us that sometimes you can have one intercept, sometimes you can have no intercepts. Sometimes you can have infinitely many, sometimes you can have a finite amount. It all depends on the problem. But when you're looking at a graph, you're looking for where it crosses the x-axis for the x-intercepts and the y-axis for the y-intercepts. But that's only if you're given the graph of the equation or if you can graph yourself. But we don't really know how to do too much of that just yet. And so how do we find x and y intercepts of an equation when we don't have the graph? So that's what I'm going to call some algebraic examples. So find the intercepts. And once again, that means find both the x and the y intercepts. For part A is x squared plus y squared minus 3y equals 4. And part B will be y equals the absolute value of x minus 4 minus 5. And so, let's talk about how we should do this. Procedure. I'm going to break this up into two things. To find the x-intercepts. So to find x-intercepts, or x-int for abbreviation purposes, if you don't mind. What do? Well, let's look back at the previous example as kind of to draw some insight on how we would do this if we don't know how to draw this. In next week, we'll learn that this is actually a circle that we can graph. But until then, how do we find out? Well, look back at these two examples. Now, don't worry, I'm coming right back to that area, but I'll get there in just a second. With regards to the x-intercepts on both of these graphs, what's something that stays consistent on all of them? So this is the point negative 4, 0. This is the point 6, 0. And this is the point 3, 0. They all have a y value of 0. And that makes sense. If you're crossing the x-axis, your y value is 0. If you're crossing the y-axis, your x value is 0. So, how do we use that to our advantage? Well, think about this statement here, or rather this statement right here. The graph of an equation is the set of all pairs x, y that satisfies the equation. You might be thinking to yourself, Phil, what the heck are you even talking about? Well, just like we found points here, we can set y equal to 0 and find the corresponding x's, and that will in fact give us points that are on the graph. In particular, it'll give us the x-intercepts. That is to say, to find x-intercepts, we're going to set y equal to 0 and solve for x. To find y-intercepts, set x equal to 0 and solve for x. Solve for y. Solve for y. My apologies. And that's kind of a nice thing. Like, if you have trouble remembering it, just remember, if you want to find an x-intercept, you need to find an x value, right? We said the x-intercepts were x equals 6 and negative 4. The y-intercepts were y equals 3 and negative 1. So you want to be able to solve for x with x-intercepts, solve for y with y-intercepts. And what I mean by solve is by any means necessary, by factoring, by using all the properties we know and love, and everything like that. So, for part A, we have x squared plus y squared minus 3y equals 4. And for our x-intercepts, we're going to set y equal to 0, which will give us x squared plus 0 squared minus 3 times 0 equals 4. If you feel comfortable just going straight to x squared equals 4, by the way, like if you feel comfortable just plugging in 0 and just doing that in your head, I encourage you to do so. That would be the easiest thing for you. It spares you getting carpal tunnel. So if you feel comfortable just omitting those because when you plug in 0 squared and 3 times 0 just becomes 0, doesn't change anything, go right ahead. But then we could use the square root property. Don't forget about the plus or minus. And then you'll get that x is equal to plus or minus 2. Those are my x-intercepts. My y-intercepts, that's terrible handwriting. My y-intercepts, you're going to set x equal to 0, and what you're going to get is, this time I'm going to show you what I mean by like just skipping this step. If you plug in 0 for x, it's just going to go away, and you're going to get y squared minus 3y is equal to 4. And as a reminder, this is a quadratic equation, and we know how to solve those. We got to bring everything to one side, factor, use the zero product rule, and all that jazz. If you need help on that, please feel free to look at the refresher videos, the little Math 96 and Math 95 refresher videos, particularly the Math 96 section on solving, factoring and solving polynomial equations. If you need any help on that, feel free to ask us. But anyways, this will be y squared minus 3y minus 4 equals 0. And you're going to factor this however you feel comfortable. This ended up being y minus 4 times y plus 1 equals 0, which gives you y equals 4 and negative 1 as our y-intercepts. Now, if you want this for reference, maybe if it's been a while, the way I got this as my answer, by using the zero product property, this means that y minus 4 is equal to 0. And you don't need to write this down if you already know it. Come on. Y minus 4 is equal to 0, or y plus 1 is equal to 0. Add 4 to both sides, that's where you get the y equals 4. Subtract 1 from both sides on this one, that's where you get the negative 1. So those are my x-intercepts, those are my y-intercepts, and that is my answer for part A. And now we'll do B. And this one's kind of fun in some ways. So this was y equals the absolute value of x minus 4 minus 5. So for the x-intercept, we want to solve for x. We want to be able to find x. So we're going to set y equal to 0. And we're going to get 0 equals absolute value of x minus 4 minus 5. And that's an absolute value equation, and the way we solve these is we get the absolute value by itself. We get x minus 4 equals 5. And then by the definition of the absolute value, this means that x minus 4 is equal to 5, or x minus 4 is equal to negative 5. And as a reminder, the reason why that works is the absolute value takes whatever on the inside and makes it positive. So it makes positive 10 stay positive 10. It makes negative 10 become positive 10. So if I made the inside, i.e. the x minus 4 equal to 5, then it would be 5 equals 5. And if I made the inside equal to negative 5, then when I took the absolute value of that, it would give me the 5. That gives me x equals 9 and x equals negative 1. So my x-intercepts are x equals 9 and negative 1. Those are my x-intercepts. And so for my y-intercepts, I'm going to set x equal to 0 and solve for y. So y is what I'm trying to find, and then x we're going to replace with 0. This is the absolute value of negative 4, which is positive 4. So this would be y equals 4 minus 5, which is y equals negative 1. That is my y-intercept. And that is my answer. So, to recap really quick, don't worry, I'm coming right back to this. This is the most important part right here when it comes to finding x and y intercepts algebraically, is that you have to set the opposite variable equal to 0 and then solve. If you're given the graph, you can just look straight at it and find where it crosses the x-axis for the x-intercept and where it crosses the y-axis for the y-intercepts. All right? And now we'll move on to the last little subsection, which is symmetry. That's right, symmetry. All right, this is going to be kind of a long definition. So definition, let x comma y be a point on the graph of an equation. The first part, like there's three subparts to this definition. The graph has what we call x-axis symmetry, which I will usually write as x-axis sim, like I'll just do the SYM because I'm lazy. If the point x comma negative y is also on the graph. So yeah, the graph has x-axis symmetry if the point x comma negative y is also on the graph. Not just the point x comma y, but x comma negative y. 2, the graph has y-axis symmetry if the point negative x comma y. So just like instead of x comma negative y, now we have negative x comma y is also on the graph. And the third one and final one is the graph has what we call origin symmetry if the point negative x comma negative y, so both of them are negative in this case, is also on the graph. Now I hope you've been suspending your disbelief for a second and frantically writing this down because I write super fast. I'm sorry about that. But what does this mean? Like it kind of looks weird when it's just this abstract, just x and y's. So hopefully this pictorial representation will help you out. So I want you to draw 3 graphs side by side. I'm gonna a graph here, and a graph here. That's what I want you to do. But I'll go ahead and get that started. So I'm gonna say pictorial representation, and so we're gonna have x-axis, y-axis symmetry. Sorry, I should say x-axis symmetry. And last but not least is origin symmetry. All right, and so I'm just going to draw 3 graphs. Don't worry about scaling it all this time because we're not actually going to be using the tick marks. We're going to create like 1 tick mark for where we want it to be. And last one like this. Boom. All right. Now everywhere around, I want you to just plot somewhat far out there value x on all of them, and the value y, the y tick mark on the y-axis, like that. And if this is x, then on the opposite side we have negative x right there, and we have negative y down here. I'm going to do that on all of them. Okay, hopefully you have all these drawn. If you don't, feel free to pause and finish it. And now we're going to draw these pictures. So, for x-axis symmetry, I want you to plot the point x comma y and the point x comma negative y. And I want you to kind of make a parabola shape, but going the opposite, like going out to the right instead of going up or down, like this. And then for the second one, I want you to plot the origin, the point x comma y, and the point negative x comma y. And then I kind of want you to make like roughly an M shape. that. And it doesn't need to be perfect, but you get the idea. And last but not least, I want you to plot the origin on the last one, the point x comma y, and the point negative x comma negative y. And then I want you to kind of make a little squiggly shape like this. Make that better. Boom. Like that. And then kind of the opposite version of it on the other side. Like that. So, when you look at it pictorially, it kind of makes sense. X-axis symmetry means that it's symmetric across the x-axis, right? This point right here and this point right here, they are the same distance from the x-axis to each other. So we've got the point, once again, we've got the point, this is the point x comma y, and they have the same x value but the opposite y value. Now this works even if the point is down here as well, by the way. Just as long as the point x comma y is on a graph with x-axis symmetry, so will the point x comma negative y. In a similar fashion, we've got these 2 points here. This is x comma y, and this is negative x comma y. And we see that they are this graph is symmetric across the y-axis, meaning that these 2 points are equidistant from the y-axis. Now, origin symmetry is kind of the weirdest one, arguably. But once again, we've got these 2 points right here. This is the point x comma y. Oh, I want to use a different color. X comma y, and negative x comma negative y. And we see, with regards to the origin right here, these points are equidistant from the origin. That's what it means to have origin symmetry. So that's a graphical interpretation of these things. And let's go ahead and do an example of those. So, let's go to the next page, and I want you to draw 3 graphs. So, example, determine symmetry. And by determine symmetry, that means determine whether it has x-axis, y-axis, origin symmetry, or some combination of the 3 of them, or even none of them. Part A, and you're just going to draw 3 graphs, and you don't need to worry about scaling at all. Part B, another graph. And part C, another graph. Hopefully you have these made, and then we're going to draw the pictures. The first one is going to look like this. Like that. The second one is going to look like this. And the third one is going to be a circle. That's a pretty bad circle, but I always screw up at the end of my circles. Anyways, okay. So, let's look at this first one. Just go down the list. Does it have x-axis symmetry? The answer is no, because look at this point right here. This point right here. Since that is a point on the graph, the same x value but the negative y value also needs to be on it, and it's not. So it doesn't have x-axis symmetry. In a similar fashion, if it had y-axis symmetry, it would also have this point over here. Point with the same y value but the opposite x value. So it's not y-axis symmetry either. And last but not least, if it had origin symmetry, since this point is here, there would also be this point down here, and it doesn't have that. So this has no symmetry. So we're just going to write none, or no symmetry. Now how about this one? Let's just pick a random point. And granted, my thing isn't drawn to scale, and so usually when you're given a graph, it's a lot easier because to see tick marks and all that stuff. This one we're just kind of eyeballing it. But notice this point right here. Let's just assume for the sake of an argument, if we took the x-coordinate, this is a positive x-coordinate, so the negative x-coordinate over here, and its y-coordinate of this point is negative, so its opposite, it's negative y, and that's kind of weird, but its y coordinate, its negative y would be up here. Let me give you an example of what I mean. Let's just assume for the sake of an argument that this is 2, negative 1. It has a positive x coordinate and a negative y coordinate. So if you try and find negative x, negative y, that would be negative 2 and positive 1. And so this has origin symmetry because this point is on here, and then both coordinates opposite version of themselves is also on this. So this has origin symmetry. You could do it just as well with like this point here. Let me grab this point here and this point right here. And once again, this is a rough sketch, so it's not perfect. It's not completely drawn to scale. But now, does it have any other symmetry? And the answer is no, because if it had x-axis symmetry, right? If it was symmetric across this line, this point would also have this. We would also have this point up here. And similarly, if we had y-axis symmetry, we would also have this point over here. But we don't. So no other symmetry besides that. And this last one, well, this point and this point are both on the graph. And again, that works the whole way around. So this definitely has y-axis symmetry. But it also has x-axis symmetry, because if you take this point, the opposite counterpart across the x-axis is also there. So it also has x-axis symmetry. And last but not least, if I take this point, the opposite version of it would be over here. And then similarly like this one over here and vice versa. So this one also has origin symmetry. As an interesting little tidbit, and we'll do this in the extra problems at the end of the lecture, but if you have two forms of symmetry, you automatically have the third. It's pretty cool, actually. But anyways, back to the thing. So that was a pictorial representation, a pictorial example. But how do we do it if we don't know what the graph is, but we're just given the equation? So what I mean here is, example, determine the symmetry of part A will be 4x plus y squared equals 4, and part B will be y equals x cubed minus 4x. So how do we do it when we don't know what it looks like? I can tell you later on in your mathematical career, you'll find ways to graph these things for yourself, but in the meantime, how do we figure it out? And so the trick, or procedure rather, is for x-axis symmetry. To test for x-axis symmetry, replace y with negative y and simplify. If you get the same equation, then the graph has x-axis symmetry. So if you replace y with negative y and you simplify and you get back to the exact same thing, that means that the graph has x-axis symmetry. And the same, in a similar fashion, and so I hope you don't mind, I'm going to do I'm going to use quotation marks for the y-axis symmetry. You're going to replace, you're going to say the same thing, but instead of replace y with negative y, you're going to replace x with negative x. And if you get the same equation, then your graph has y-axis symmetry. Last but not least, for origin symmetry, the same thing, right? But you're going to replace x with negative x and y with negative y. And then you'll get origin symmetry. I hope that makes sense. So basically, it's the same verbiage, it's the same sentence, except instead of y with negative y, x with negative x, and then instead of x-axis symmetry, y-axis symmetry, and the same thing for origin symmetry. Now, why does this work? Well, once again, if we go back to the definition, the x-axis symmetry is if x comma y is on the graph, then so is x comma negative y. Which means that xy is a point on the graph, so that solves the equation. And since x comma negative y is also on the graph, x comma negative y also solves the equation. So it should make a true statement. So let's see what I mean. Let's get an example. Let's go to part A. So solution. Part A, we have 4x plus y squared equals 4. So let's try x-axis symmetry. X-axis, you're going to replace y with negative y. So x stays the same, but y gets replaced with a negative y squared. And remember that negative is on the inside of the parentheses. Don't put it on the outside. Because when you square negative y, you get 4x plus y squared equals 4. That's the same equation. So that means we have x-axis symmetry. So when we plugged in x and negative y, we got the exact same equation. And that means that it has x-axis symmetry. Let's try it for y-axis. Well, with y-axis symmetry, you're going to replace x with negative x. So this becomes 4 times negative x. And y stays the same, so it's plus y squared equals 4. And simplifying that, we get negative 4x plus y squared equals 4. Now that's not the same equation. That's not the same equation. So that means not y-axis symmetry. We do not have y-axis symmetry. And last but not least, we'll check the origin. And that's where you change x to negative x and y to negative y. So we get 4 times negative x plus negative y squared, negative y inside the parentheses, equals 4. And then we get negative 4x plus y squared equals 4, right? The negative y quantity getting squared makes it a positive y squared. 4 times negative x is negative 4x. Same thing, not the same equation. Which means not origin symmetry. And that is our answer. So it has x-axis symmetry only. Now, because I don't want the lecture portion of this one to go too much longer, because it's already been, like, you guys are troopers for sticking around for this long, I'm going to just put the answer on the next, for part B, up on the board. I'd like you to try it yourself. And so go ahead and pause the video and try and figure it out for yourself, and then redo it when you finished. And so we'll go ahead and go to the next page. And I'll make a couple comments here on this one. So it has origin symmetry only. A couple things to note is that negative x raised to the third power, that's an odd power, so that's negative 1 to the third power, which gives you, that's why we get the negative x cubed. And then negative 4 times negative x gives you the plus 4x. So that's how that works. And the reason why origin symmetry exists on this equation is that when you replace x with negative x and y with negative y, like I've done here, you get negative y equals negative x cubed plus 4x. And that doesn't look like the original equation, but if you were to divide both sides by negative 1, this negative y divided by negative 1 gives you positive y. Negative x cubed divided by negative 1, that becomes positive x cubed. 4x divided by negative 1 gives minus 4x, and we're back at the original equation. So that's why I've got that check mark there. So sometimes you might need to divide both sides by negative 1, which is kind of a tricky thing. But that's that one. And that will do it for the lecture portion of this video. Now we're just going to go on to some extra practice problems. So here are the extra practice problems. Feel free to pause it and write them down if you'd like. For reference, these are the points negative 3, 0, 0, 4, and 3, 0. So we'll go ahead and get started with part A. Part A of question 1, that is. This one. Find the intercepts and determine symmetry. So, solution. For the x-intercepts, Like, we could graph this, honestly. If you remember how to draw lines, you could graph it right now. Or you could do a couple things. But we're going to talk about lines next week. So right here, we'll just use our x-intercept stuff. So we'll do our algebraic version. For an x-intercept, you want to set y equal to 0. So 2x plus 3 times 0, that just goes away, minus 7 is equal to 0, which gives us x equals 7 halves. And our y-intercept, we're going to set x equal to 0 and solve for y. So we get 0 for, when you plug in 0 for x, this goes away, and you just get 3y minus 7 is equal to 0, which gives you y is equal to 7/3. So that's my y-intercept, that's my x-intercept. Then we're also going to test for symmetry. So x-axis symmetry. When you're trying to find the x-axis, and if you ever forget, you can always draw a picture. X-axis symmetry means we're symmetric with regards to this line. So if I have a point up here, I have this same point. If this is the point x comma y, they have the same x value, but the opposite y value. So when you're testing for x-axis symmetry, you're going to replace y with negative y. So 2x plus 3 times negative y minus 7 equals 0. That gives you 2x minus 3y minus 7 is equal to 0, and that is not the same thing. We originally had 2x plus 3y, now we have 2x minus 3y, so it's not the same thing. So it does not have origin x-axis symmetry. How about y-axis symmetry? Well, 2x, 2 times negative x plus 3 times y minus 7 equals 0. So replacing for y-axis symmetry, you're going to replace x with negative x. See if you, and simplify. We'll get negative 2x plus 3y minus 7 is equal to 0. And once again, it's not the same thing, so it doesn't have y-axis symmetry. Last but not least, origin symmetry. We'll replace x with negative x and y with negative y. So 2 times negative x plus 3 times negative y minus 7 equals 0. You get negative 2x minus 3y minus 7 is equal to 0. And it kind of looks like it might be the same thing, so you could try and divide both sides by negative 1. But if you do that, you'll get 2x plus 3y, which is looking good, but then you'll get plus 7, and that won't be the same thing. So this also does not work. So no symmetry. No symmetry. And that is part A. And we'll move on to part B, which was this graph. And so with this one, x-intercept, y-intercept, does it have any? And if so, what are they? And then symmetry. What symmetry does it have? So the x-intercepts are where it crosses the x-axis, which would be right here and right here. So that will be x equals negative 3 and positive 3. And the y-intercept is where it crosses the y-axis. So in this case, that would be y equals 4. So that's our x and y intercepts. And because the arrows are pointing upward, this will never go and pointing out that way. It'll never come back in to cross the y-axis again, and it'll never go back down to cross the x-axis again. So those are the only x and y intercepts. And then with regards to symmetry, it doesn't have x-axis symmetry because if at this point would also have to have this point, we'd also have to have that one, which we don't. And then it doesn't have, my bad. It doesn't have origin symmetry because for this, for like this point, we'd also have to have this point here, and we don't. But we do have y-axis symmetry because this point and this point are both on the graph. It's symmetric with respect to the y-axis. So it has y-axis symmetry, and that's it. And that is our answer for part B. So that one was pretty nice. Now we'll move on to this one. If a comma negative 5 is a point on the graph of y equals x squared plus 6x, what is a? Now that's a really, really fun conceptual problem. So we have to remind ourselves what it means to be a point on the graph. It means that this point satisfies the equation. That is, this statement right here says that when x equals a, y equals negative 5. That's what this means. You could say it the other way too, when y equals negative 5, x equals a, but it doesn't matter. That's what that statement means. So if we're trying to find a, we'll use this information to plug in for y and x. So y is -5, and x is a. So we get a squared plus 6a. And that's a quadratic equation. And we can solve for a. Primarily, we can move the 5 over. We get 0 equals a squared plus 6a plus 5. And then you can factor it however you want. Remember to watch those videos if you need a little bit more practice on factoring. But this will factor to a plus 5 times a plus 1, which gives us the possibilities that a could either equal -5 or -1. So remember, when you set this equal to 0, subtract 5 both sides, and you get that -5. By the way, like, you can write this on the side if you want. This is a plus 5 equals 0, or a plus 1 equals 0. I'd encourage you to get to the point where you feel comfortable skipping this step, by the way, and just coming to the answer right there. So I did that one very, very quickly, but I wanted to make sure I mentioned, like, the trick here with all these really, like, whenever you see a problem that you don't really understand right off the bat, don't panic. I know it's very easy to, especially with mathematics. We all get very scared, myself included sometimes. So, like, I'm victim of this too. But try and ask yourself, what do you know? What are you trying to find? What do we know about the fact that a comma -5 is a point on the graph? What can we use that for to figure out what a is? So that's part 2. Last but not least, we'll come to my favorite question. Honestly, what's really fun is I actually thought of this problem. I haven't seen it in a textbook, and one of my first or second semesters teaching, I thought of this problem, and it was really, really fun, and my students really enjoyed it. So, show that if a graph has 2 types of symmetry, whether it be x-axis and origin symmetry, or x-axis and y-axis symmetry, or some other combination, show that then it automatically has the third one. So, this is, like, technically speaking, we'd be doing what we call a proof here. And if you like this problem, by the way, if this satisfies an itch for you, you might want to try and study more mathematics in the future. I think this is pretty cool. So, technically speaking, there's 3 cases to figure out. There's, what if you want to show that if you have x and y-axis symmetry, that you also have origin symmetry. You want to show that if you have x-axis and origin, then you have y, and if you have y and origin, then you also have x. But they all boil down to the same argument. So we're just going to say, we're just going to show that x-axis and y-axis symmetry implies origin symmetry. We're just going to do that case, and I can guarantee you the other 2 cases are immediately the same. So, we want to show, to show origin symmetry, we need to show that if x comma y is on the graph, then -x comma -y is on the graph. Right? That's what origin symmetry means. If you have x comma y on the graph, then -x comma -y is also on the graph. That's what we need to show. So, we're going to let x comma y be a point, be on the graph. Since we have x-axis symmetry, we also have the point x comma -y on the graph. Right? That's what it means to have x-axis symmetry, is if you have a point, then the point with the opposite y-coordinate is also on the graph, right? So we have x-axis symmetry, which means we have the point x comma -y. Then, since x comma -y is on the graph, and we have y-axis symmetry, we also have the point -x comma -y. And we're done. Voodoo! I'll explain what I mean in just a second. So why did that work? Well, what was going on in that last sentence? So the reason why I said and we're done is that I just showed that we also have this point negative x comma negative y, which is what we were trying to show. That if we start with the point x comma y, we show that we have negative x comma negative y, which is what we did. So what does this last sentence mean? So it means, like, this is a point on our graph, right? So if that's a point on our graph, since we have y-axis symmetry, we have the same point but with the opposite x-coordinate and the same y-coordinate. So same y-coordinate, but opposite x-coordinate. And that's how we use the second part of it. That's how we use the y-axis symmetry. I think it's a really cool problem. So now you can use this as fact if you want. So if you know you have two types of symmetry, you don't have to test for the third. You can just automatically claim it. And that kind of correlates back to this one. If you remember, way back when, don't worry, I'm coming right back to that page. But this problem right here, we had x-axis symmetry, we had y-axis symmetry, and by automatically we have origin symmetry. So you don't need to show the third one. Pretty cool. So here's this again. Sorry about that. So pretty cool problem. You're never going to be tested on this type of a problem. This is proofs. This is the start of an area of mathematics that has to do with proving things, and that's more for upper division mathematics, but I just wanted to give you a taste of what you might see in upper stuff. I hope you enjoy, and I'll see you next time.